We're going to talk about bioretention siting, design, and construction. First off the bat is we're going to talk about siting, go through some of the infeasibility criteria around siting, and then move into design. So I think as we've seen, bioretention can either be of the infiltrating type, where it's infiltrating into the native subgrade, or it can be non-infiltrating, where we're infiltrating our stormwater through the treatment media, but not necessarily into the subgrade, like these two examples here showing where if we have inadequate native infiltration rate in our subsoil, or we're putting a liner in because we do not want to infiltrate because of slope stability or infrastructure protection or whatever reason, we are deciding we have an underdrain. So there's different siting criteria when we have these non-infiltrating type, or you can see like the planter, which can be on structure or integrated into architecture into the building, versus where we have different siting considerations where we've got bioretention that is of the infiltrating type, where we are infiltrating into native subsoil, and then we've got groundwater implications for that. And so one of the chief design criteria that many of you know is around dealing with both our infiltration rates of the native subsoil and vertical separation to seasonal high groundwater levels. And so one of the first infeasibility criteria or design considerations, depending how you look at it, is really about what is our vertical separation to groundwater. And there's essentially two criteria that are in the manual around feasibility. One of them applies if you've got relatively small contributing areas, and the other one applies when you've got relatively large contributing areas, and that is essentially related directly to groundwater mounding. And so the idea is that if you have a bioretention cell where you've got this set of criteria, meaning you've got less than 5,000 square feet of pollution generating impervious, 10,000 of impervious, meaning roofs if it's not pollution generating, or pedestrian areas, or 3/4 of an acre of lawn or landscaped area, you can, going to a bioretention cell, you can use the only 1 foot of vertical separation from the bottom of the cell to the seasonal high groundwater level. And so that's because the idea there is it's reflecting the idea that a smaller groundwater, localized groundwater mound would develop under those scenarios than in a much more centralized bioretention cell where we have greater than that amount of contributing area, and then we need to go to 3 feet. And so that's a relatively new change with the last manual. It used to be 3 feet in a lot of cases, and so, but that's something to be aware of. And these are all, of course, in the manual, but assessment of the seasonal high groundwater table, of course, is going to be a key consideration. Another infeasibility criteria is around slopes. As we know, introducing a lot of water into native soils around certain slopes can lead to instability. So that is horizontal separation to slopes for infiltrating facilities is key, as well as landslide hazard areas. And groundwater protection areas is an interesting one. It is on the list. However, bioretention in certain groundwater protection areas can be seen as having sufficient protection for groundwater resources. Certainly, it's something that needs to be considered, and any specifics of that particular groundwater protection area needs to be considered. But for example, on our work, we routinely use bioretention for treatment and then go straight to a UIC, an underground injection control well. And so bioretention is typically seen as being sufficiently protective of groundwater in those cases. However, it is something that you need to be aware of. And then horizontally, a lot of these criteria are similar that you would see for septic systems, but the 100-foot setback for drinking water wells or any springs used for drinking water, soil contamination, and so forth are all in the manual. And so it's not to say these are criteria. I think in the presence of professionally developed analysis, some of these may be able to be adjusted, some may be greater or some are less, but these are generally presented in the manual as guidelines to local jurisdictions on the review and permitting of these systems. Others that are in the manual include even separation to native growth protection areas so that we don't oversaturate tree roots and this sort of thing. Here we go again with slopes. Other slopes, are considered more aggressively than this. Another slope criteria, underground storage tanks and the like. And so these are all in the manual. What we really want to understand in particular is with our infiltrating facilities, it's critical to understand the fate of the infiltrated water. And so just getting the water to infiltrate without an awareness of what the fate of that infiltrated water is really inadequate. That is to say, if you're in a slope situation, it could break out in a slope. And so we want to know that if the water that we infiltrate is going where we intend, meaning into the shallow or deep groundwater. If, for example, if you've got a dense amount of infrastructure, we want to know that if we're infiltrating water, it isn't just going to find that sewer trench, run through the pea gravel, run down the hill and break out in somebody's front yard or undermine a road. If we've got potential for infiltrated groundwater to break out in different places, we really need to be aware of it. And so there are ways to deal with, and particularly the trench, putting in trench dams, bentonite, or some kind of a liner or some other way to prevent that infiltrated water from popping out in places where we don't expect. Another siting consideration is really about siting these facilities, bioretention and rain gardens, into the site. And we have a whole intermediate level course on, in general, we want to look at preserving native vegetation and natural flow paths right off the bat like we would on any site. Really being aware of longitudinal slopes and cross slopes, because bioretention facilities need to be put in flat. As we encounter slopes longitudinally and cross slopes, that has a lot of implications for the size of the cut or the retaining wall that may be needed and so forth. Setbacks to utilities and other infrastructure, wetlands, and so forth. So these are all criteria that we need to consider. Back to the soil, the native soils really do drive the siting of bioretention quite a bit. We really do, like Curtis, really want to seek out those areas on the site that infiltrate particularly well and site our bioretention cells there where we can, because that essentially is going to lead to a cost-effective design. So when we think about the new low impact development requirements as part of the new permit, and we think about the requirements to utilize low impact development strategies where they are feasible, there's another level to that where it behooves the designer to understand the site well, because that's going to allow you to not just put the LID facilities in where feasible, but also put them in the most cost-effective way. So having an inadequate sense of the soils on your site, meaning you're coming in with maybe an old school typical geotech approach, which might pop a few holes mostly for bearing capacity, and don't really understand the kind of complexity of the distribution of soils on your site, is going to typically lead to a less cost-effective design in my experience. And so what I advocate and have done on my work for a while is really taking more of an on-site septic approach when evaluating a site for bioretention. If you have a site where you are going to rely on on-site septic for your wastewater disposal, you wouldn't conceive of coming in and doing your site layout without really understanding where your soils that are going to meet the Department of Health criteria for wastewater. So it's really about approaching a site from a stormwater point of view that's a very similar way. So reconnaissance level soil assessments with hand tools, verifying maps, really spending much more time on the analysis. And if you do that, you're going to find that your LID site designs are going to be a lot more cost effective because your facilities are going to be smaller. So anyway, so we're capturing that soil variability. And then we're going to go out and we might do some initial infiltration rates based on some quick assessments, maybe some textural analysis at a planning level of analysis. And then once we've got our design worked out, we really come back and remobilize and get our design level information. So when working with native soils, we also want to consider the minimum feasible infiltration rate. First of all, if we are working in a basin where we're not going to infiltrate, I'm working on a project now in the north part of Seattle where we're specifically not going to infiltrate because of very large slope leading down to Puget Sound, and so our facilities are purely for flow attenuation and treatment, and so they're lined, and so therefore our native soil assessment, needless to say, is pretty minimal. But where we are going to design infiltrating facilities based on those infiltration rates, we want to be aware of the infiltration rate that we need for design. Now, there's in the manual, there is the minimum feasible initial infiltration rate of 0.3 inches an hour. So that's in the manual, and that's really a guide to local jurisdictions to say if we run our pit test and we get less than 0.3 inches an hour initially, then typically bioretention is not required in those cases. However, that is not the minimum technical feasibility infiltration rate. So it's important to keep that separated. So what is required from a regulatory point of view to meet the LID to the maximum extent feasible criteria means that the manual does not require you to install bioretention for flow control in the cases where you've got less than 0.3. However, it doesn't mean that you can't do it. It's perfectly technically feasible to install bioretention in infiltration rates much lower than that. It's just not required. And so that's important to keep in mind. So these facilities can work well on lower infiltration rates as long as we've done our proper site assessment and our proper analysis in terms of measured infiltration rate, and we're basing our design on those numbers. It's fine to work in infiltration rates lower than what's stated here. And so a little note on soil variability. So I mentioned that the type and extent of soils analysis that is done on a LID site in the current manual approach really needs to be a lot more nuanced. And so this is just an example from Seattle. This is Broadview Green Grid, which is one of their green stormwater infrastructure projects in Seattle. You see a couple of blocks there. We're going to look at the soils from these 3 sites. So you can see site 1 and 2 are a half a block apart. Site 3, almost the same distance, a couple blocks the other way. And so we're going to look at the soil here of site 1. Beautiful loamy soil, real nice looking, pretty much an ideal infiltration soil for bioretention probably. Now we're going to look at site 2, not that far away, probably about a half block, pure sand. Completely different site condition here. And then of course site 3, just to kind of complete it, till in site 3. So these are all within less than a block of each other in one little project in Seattle. So this is hopefully making the case that really a much more nuanced site analysis is necessary, because if you looked at your NRCS maps and it told you you had something like any one of these, and then you did a 1 or 2 test pits to verify it and it happened to be right, and you happened to find that same stuff, you would have missed the other 2. And so it's very, very important to understand that. So in addition to assessing our soils, they also need to measure our infiltration rate. So we're going to spend a little bit of time now talking about the currently approved methods for assessing design infiltration rates of the native subsoil under the current manual. And at the largest view, what we're doing is we're going to go out and we're going to take a measurement of how fast the water goes into the ground, measuring the saturated hydraulic conductivity. Then we're going to apply a series of correction factors, and then we're going to get our long-term rate. So we're going to take what we measure in the field, apply these factors to get our design rate. We design on the rate only after we've applied all the factors. So some of you may know, as the manuals have evolved over the past few years, there's been a historic use of even USDA textural classification. So we'd go out there, we'd run our sieves, we would get a textural classification, we would say, okay, it's sandy loam, and then you would just develop a rate based on that textural analysis. I guess fortunately is in our rearview mirror as a region as an acceptable way to develop a design infiltration rate. We also have used in the past grain size analysis. So looking at running a set of sieves or particular sieves and looking at the relationships of the particle sizes and developing a rate from that. That remains in the manual, however, only in certain cases, and we'll talk about that in a second. And then, so these are based on stuff we can run in the office. And then out in the field, there's some historic tests here. We used to use the old EPA falling head or the double ring infiltrometer test. There are the pit tests, the small scale and the large scale pit. Where we are today with the current manual is that the textural classification is put to bed. That's no longer in use. We can use grain size analysis, but only for soils not consolidated by glacial advance, meaning essentially our outwash soils. So it is acceptable currently that if you have a site with outwash soils, unconsolidated, that you may develop an infiltration rate based on grain size analysis with the appropriate correction factors. Double ring test and the EPA falling head are also retired. The tests we're going to do in the field are the small scale pit and the large scale pit. I'm going to roll through the small scale pit procedure. The large scale pit is essentially the same. The large scale pit is used on where we have large contributing areas. I mean, the small scale pit is really all we need to do for low impact development sites, because it is intended for sites that are relatively dispersed and smaller scale. The small scale pit can be used in lieu of the large scale pit on large sites if you also have really granular soils that are going to infiltrate really, really fast, and doing the large pit is just sort of going to require a lot of water, more water than you have.